let me give a brief outline of the construction of induced representations. If I have a subgroup H of a finite group G, and I start with an H representation, phi, I'd like to construct a G representation, psi, so that its character is the induced class function. So I'll just sketch the argument and I'll leave some details for the notes. So I'll just tell you how to build it. So first I have to tell you what this vector space W is. It's going to be a space of functions. I'm going to look at functions from the set G, the underlying set of the group, to the vector space V, which is the space of the original representation. But I'm not going to take every function. I'm going to look for functions omega such that omega of hx equals phi sub h of omega of x for all h and h, x and g. This is called a space of h equivariant functions. The group H acts on the left on the group G, but it also acts on the vector space because it's a representation of H. This is itself a vector space, as you can easily see. If you add two things of that type, it's still of that type. Let's notice, and I'll introduce some notation here. I'm going to use this R equal x sub I, collection of x sub i's, for the set of representatives of right H cosets in G. I want to notice the values of omega are determined by the collection of values of omega on representatives, on a choice of representatives. You can get every other value uniquely, in fact, from that. You can compute everything. In fact, it turns out that because of this, the dimension of W is equal to the product of the dimension of V times the index of H and G, which is the number of right cosets. All right, so we've got a vector space. Now we'll define a representation. And we'll define psi going from G to the general linear group of this larger vector space by the formula psi sub G of omega. Well, I have to say what that is. That's going to be another element of W, so it's another function, an element in here. So I have to say how you evaluate it on an element of the group. So omega is in W. G, of course, is also in G. And the formula is you take omega of x times G. That's the definition. You have to check that this is, in fact, a representation, that it's a homomorphism. It's routine, a little confusing to do. All right, we got our representation. I claim the character is what I want it to be, so I have to figure out how to compute that. Okay, so I have my space W of H equivariant functions. For each right coset inside G, I'm going to consider a subspace, which I'll call W sub Hx. That's defined to be the collection of functions in the space which are supported on that coset. So what that means is that if I evaluate it at an element of the group that's not in the coset, I should get 0. The only way to get a non-zero value is if I plug in something that's in the coset. So I'll call that the space of functions supported on the coset. Here's a fact you can prove. W, the vector space, is a direct sum of the collection of subspaces. So I can write W as the direct sum of WH x1, direct sum dot 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 up through WH WHX, let's say M, where I'm using here this set of representatives of right cosets, which I'll number from 1 to M. Okay, that's not hard to prove either. Now here's the key observation. If I take my new representation I defined called psi, and I plug in elements of W sub hx, it turns out I always get elements of W sub h xg inverse. So psi g always sends all the elements of one of these subspaces to one of the other subspaces. In particular, I want to pay attention to when it goes to the same subspace. So psi g of W sub hx is actually going to be in W sub hx if and only if xg x inverse is an element of H. That conclusion you can read off from the first statement. Let me prove this one. It's almost immediate. So if I start with an element of WHX, so that means that it's 0 if y is not in that coset. Let's let omega prime be psi g of omega. Now if I have a z, which is not in H xg inverse, and I plug that into W prime, by definition, that's psi g of omega of z. Remember the definition of psi g, that's omega of zg. If z is not in that coset hxg inverse, then zg is not in hx. And by assumption, that's going to be 0. That's the proof. So what does this mean? Well, what it means is that the psi g basically has a block decomposition in terms of this direct sum decomposition of the subspace, of the vector space. So I can write psi g as being built out of blocks, each of which is a linear operator. Let's call it psi 11g, psi 12g, psi 21g, and so forth. Psi ijg is an operator that goes from whxj to whxi. So when we write an operator as a matrix, we're doing this with one-dimensional subspaces, basically. Now we're just doing it with blocks. So why is that important? We want to compute the trace of psi g, and when we do that, what's going to be relevant are the blocks which are along the diagonal. The trace of psi g is going to be the sum of the traces of each of these operators, psi I sub g, where the two indices are the same. But hey, in a lot of those cases, that's going to be 0. You're only going to get a non-zero block if the target space is the same as the source space here. And we saw that only happens under certain conditions. So we're actually going to get a sum over the representatives of right cosets such that xig xi inverse is in the subgroup H. And then what we're computing is the trace of psi g restricted to that subspace corresponding to those cosets. We can throw away the other blocks on the diagonal because the operator is 0 on those. Well, finally, there's a calculation. We can define a linear map, which I'll call EX, from WHX to the original vector space V, and this will just send a function to its evaluation at the element X. That's an isomorphism of vector spaces, as you can check. And then we have the following consequence. If we have elements of the group with this property, that xgx inverse is an H, then the value of psi g on the subspace WHX is equal to, well, it's really a conjugate of the original operator for the original representation on V, conjugated by this isomorphism EX. Again, you work out what this means. It's just like a one-line computation to show this is true. You just have to unwind the definitions. But now we're good because we can compute the trace of that. It's the conjugate of something, so it's the trace of that. And I plug it into that formula. The trace of psi g is going to be the sum over these representatives which conjugate G into the subgroup H of the trace of phi xi g xi inverse. So that'll be exactly the formula I want. I'll get chi psi of G equal to the sum over the same stuff of chi phi of that conjugate of G. That was literally the formula for the induced character. That's, in sketch, the construction of the induced representation.